confidence interval for the population mean mu. We saw from the sampling distribution that from a population with a mean mu, we repeatedly take random samples of size n and compute the mean for each of the sample. Again, these samples have the same size n. We obtain many of these sample means x1 bar, x2 bar, x3 bar, and so on. Then from these sample means, we investigate their distribution. We saw that although due to sampling variability, x1 bar, x2 bars, x3 bar might not be the same, but they are very close to the population mean. That is, the sample mean x bar is approximately the same as the population mean mu. Now we turn this around and we say, well, normally we do not have the information for the population mu, so this time mu is unknown. The population mean is unknown. However, from this population, which is large, we can obtain a representative sample and we compute x bar. X bar is the mean of the sample only. And if we have a good unbiased sample and with good study design, then we can say that this sample mean estimate the population mean. And so we call x bar the point estimator for mu. The specific value of x bar, a numerical value, equals an estimate for the population mean. This is what we call a point estimate. Now, there is a problem with this point estimate. Suppose the mean unknown is somewhere in the middle of the population distribution here. And when we compute x bar, we might not get the same value of this unknown mu, but again, these x bar are very close to mu. In fact, with the normality conditions are satisfied, we will see a bell-shaped curve. And so if we were to use one single value x bar, each dot represent x bar here, we might make a mistake of not getting the correct unknown mu, because x bar, although they are close to the center unknown mu, they are all over the place. Having only one single number, a point estimate, to estimate the unknown mu, will leave out many more. And so instead of using one single value, we now use an interval. Suppose we obtain a good sample and we compute x bar. Although x bar might not be exactly mu, we're going to use an interval, but the question is now, what interval? How far out from that x bar value do we need to go? Well, we will use the standard deviation rule that says 68% of the distribution will be within one standard deviation away from the mean, 95% of the distribution are 2 standard deviations away, and 99.7% are 3 standard deviations away from the mean. Anything that is within 2 standard deviations away from the mean is considered as usual. And so we will use a 95% interval. But the 95% interval means that from that estimator x bar, we will add 2 standard deviation to the right, and we will subtract 2 standard deviation from x bar to go to the left. This will give us an interval x bar minus 2 sigma, x bar plus 2 sigma, and sometimes we write this as x bar plus or minus 2 sigma. Now, we mentioned the condition for normality. The central limit theorem guarantee that we will have an approximately normal distribution if the sample size is greater than 30, if the original distribution was not normal to start out with. And so from the sampling distribution, these standard deviations are actually the standard error. So they should be sigma x bar. What is sigma x bar? Sigma x bar is the standard deviation of the population sigma divided by the square root of n. And so we will construct the confidence interval for the unknown population mean with sigma given, meaning somehow we know the standard deviation of the population, and this might be from the historical data. And so to summarize, to construct the confidence interval, we will need to check the normality condition. We will compute x bar, which is the point estimator. We will compute the standard error. Once we have these, we will take x bar minus 2 times the standard error, and then x bar plus 2 times the standard error to obtain the confidence interval. This is what is known as the 95% confidence interval. Of course, if we want a 99.7% confidence interval, we would need to multiply the standard error by 3, because 99.7% confidence interval is approximately 3 standard deviations away from the mean. In this case, with the 95% confidence interval, after we construct the confidence interval, we state that we are 95% confident that the unknown population mean mu falls within 2 standard error of the mean. Remember that x bar minus 2 times the standard error is less than or equal to the unknown mu, less than or equal to x bar plus 2 times the standard error of the mean. The number 2 in this formula represents the number of standard error. In general, we construct a 95% confidence interval, but in some cases we might construct 80% confidence interval, 90% confidence interval. Regardless, the formula will be x bar plus or minus z times sigma, the standard deviation of the sampling distribution or the standard error. What is z? Z is the corresponding z-score for the confidence interval. For the 95% confidence interval, we will find that the actual z-score is actually 1.96, and that is very close to the number 2 that we use. We use 2 because the standard deviation rules say that 95% of the data falls within 2 standard deviations away from the mean. But again, the actual z-score is 1.96 for 95% confidence interval. If we were to construct an 80% confidence interval, then we don't expect z to be 1.96 anymore.